Hello everyone, welcome back. This is Fluence's Tech Talk number 2, our topic, digestates. For those of you who've been following our Tech Talk series, you've already heard me talk about anaerobic digestion. So today, it's time to turn our attention to what happens on the backside of the digesters. So here we go. So what do we mean by digestate? Well, digestate in simple terms is the treated effluent that's discharged from the digester process. So recall from our digester tech talk that we discussed the types of digester projects. These can be regional food waste, manure-based, specific individual industrial wastewaters, or municipal biosolids. So the quality of the digestate will be different between these systems. In most cases, though, digestate will contain a residual nutrient load. So we know that from our Tech Talk, digesters do an excellent job at reducing the organics, but they do very little in the way of nutrient reduction. Actually, what they do is they assimilate and kind of change the form of the nutrient. So the digestate quality is going to change from project to project, but typically these systems will all have an effluent that contains a nutrient-rich solid part and a nutrient-rich liquid part. Typically in food waste and manure projects, it's possible to separate these into the solid phase and the liquid phase. This is also true for certain industrial settings, but not all industrial settings. The solid phase is normally used for agronomic value. That is, we make a biofertilizer. Most farms and crops can readily accept this type of biofertilizer. The liquid fraction, however, can create additional challenges. This is primarily due to the volume. It can become problematic or even expensive to dispose of the liquid portion, so we're left with one of three options. We either send it to a municipality, we treat it on site, or we further process the liquid fraction such that we're extracting every ounce of beneficial nutrient out of the system into a liquid biofertilizer. As you heard me talk about in Tech Talk number 1, the environmental and logistics drivers will create differences at every site, so this is why we find so many different methods of digestate treatment. So, why is digestate treatment important? Well, a few reasons why. Number 1, it allows for direct discharge. So this can be a more holistic and cost-effective method versus physically hauling all this liquid digestate. So by direct discharge, we mean either to the city, municipality, or surface water, or even irrigation. Number 2, it helps us meet environmental regulations. So this could mean, again, meeting those POTW discharge limits, or meeting surface water, or getting to a point where we can actually irrigate all of this water at the end. Number 3, it also removes other pollutants like salts and metals that are not beneficial. Number 4, it allows us to biologically convert certain nutrients into forms that can be captured and put to beneficial use in other areas. And number 5, it helps to reduce the impacts to cities and landfills. So we're not hauling as much, we're not overloading the municipal sewer systems, the municipal wastewater plants, etc. So for all these reasons, this is why it's crucial to consider and to have digestate treatment on site. Okay, before we get into the latest and greatest technologies and digestate treatment options, I wanted to identify a few assumptions in the industry. So this is based on our experience. Here I've listed the top 5 and we'll go through one by one. There are likely other assumptions out there, but again, this is based on our experience. So assumption number 1, digestate can be sold or it can be given away. So most digestate is going to have great agronomic value. It's going to have nutrients. So yes, generally speaking, digestate can be given away. Selling digestate is a whole different animal. Most likely, you're not going to be able to earn an income on the digestate, and that's for several reasons. Number 1, just the physical movement and all of that sludge and all that liquid can be costly for the people that are picking it up. So don't always assume that you're going to earn money from the digestates. As long as the local regulations and the crops allow, most solid digestate can be given away. Some portions of liquid digestates can be given away. But there are 2 key points here. In almost all cases, you're not going to be able to discharge raw digestate, untreated digestate. You need some type of further processing. So this is going to require the solids liquid separation phase that we've already talked about before it's feasible to physically move the digestate around. So this can be as simple as dewatering, or it can be as complex as filtration in some cases. Depends on feedstock, depends on the digester strategy and the efficiency of the digester. Secondly, not all facilities have logistical advantages. That means they may be in the middle of nowhere. Maybe there is farmland, maybe there's not farmland, maybe they're in the middle of a city. So we find that many facilities require more advanced processing on site to a point where they can allow continuous discharge while separating the solids and doing something else with the solids. So don't always assume that digestate can be sold or that it can be given away. Common assumption number 2, digestate quality is the same. Now, when I say the same, I mean within a specific industry. So let's use dairy as an example. We see a lot of people assuming that the digestate quality is going to be the same from dairy facility number 1 to dairy facility number 2 to dairy facility number 3, etc. It's not always the case. Yes, you can lump them into, let's say, a general range, plus minus 30%, but the scale of the operation, the feed combinations, the product combinations, the local logistics are likely different from one facility to the next. So these combinations can create different efficiency for the digester and a different set of design considerations for the digestate treatment. The dairy industry is an industry that's used anaerobic digestion for decades. Some of these facilities process waste differently. Sometimes they separate high strength, sometimes they separate the low strength. So some facilities are remote, the logistics are different. Some facilities are a major contributor to the local municipal system while others aren't. So this impacts how they view digestate treatment and what can go down the drain. The point is that when systems take in various and varying conditions, the digestate is going to change. So it's not always safe to assume that digestate is going to be the same from project to project. Okay, common industry assumption number 3. Project infrastructure can be copy and paste. It can be duplicated. It can be replicated. It can be copied from one project to another project. That's what we mean here. The short answer is no. Rarely are two projects ever exactly repeatable. Whether it's the environmental standards or the regulatory landscape, treatment goals, literally the physical site conditions, there are always differences that require some modification from an existing project to a future project if you're trying to utilize the same treatment scheme. So don't get me wrong, we routinely use past projects to estimate future projects, but 9 out of 10 times there's going to be a difference in the tank or a difference in the dewatering mechanism, a difference in the hydraulic retention time, a difference in how much ammonia needs to be removed, phosphorus, etc. So a lot of different reasons why you cannot always copy from one project and directly duplicate in another project. All right, common industry assumption number 4. Costs are linear with volume. And when I say volume, I'm talking about volume of digestate here. So the short answer is, to some degree, costs are linear. But really small facilities and really large facilities can really skew the economic curve. Most facilities in between, so your average facility, will have a relatively linear cost to volume ratio. However, the linearity stops when we start to compare the strength of digestate from one project to another. Some facilities will literally have 10 times the amount of nitrogen that another facility has. Some facility will have 10 times the amount of calcium that another facility has. So the cost can be driven more by the strength of the digestate because of the requirement to adopt a different technical solution based on that specific strength. Some technologies are better applied to nitrogen removal, while others are required to deal with the ionic activity in the water. So this is why one technology may be more economical at one scale, but less economical at other scales. And last but not least, we have assumption number 5, and that is that, hey, I can just send my digestate to POTW untreated. That is, I can put the digestate down the sewer line. First and foremost, it's highly unlikely any municipality is going to agree to that just because of the simple fact that you're going to overload their system. So for the sake of argument, let's try to put this into perspective. Let's use a regional food waste digester facility. The digestate COD value is 13,000 milligrams per liter. The ammonium value is 2,000 milligrams per liter. Let's say this facility is producing 60,000 gallons a day of digestate. The equivalent COD load to that municipality is almost like having an additional 1 million gallons a day of flow. the equivalent ammonia load to that municipal facility is almost like having 3 million gallons a day of additional load. So in other words, that 60,000 gallons a day is more like having a 1 to 3 million gallon facility in terms of the total pollutant load. So this is why digestate can seem very costly to treat, because you're basically having the same pollutant load as a small city. So let's try to put this into another perspective, and that perspective is that you're going to choose to haul all of this liquid digestate off-site. So at 60,000 gallons a day, your average tanker is going to carry about 6,000 gallons if you're lucky. Most tankers are going to cost you $1,000 per haul. So that's 10 trucks a day, that's $10,000 a day. That adds up to almost $4 million on an annual basis. So the last perspective here is, let's assume that the municipality did agree to take your waste untreated, but the agreement is there's going to be a surcharge. So typically municipalities surcharge based on flow, BOD, COD, TSS, TKN, phosphorus, and maybe a few other things. So by the time you add all of this up and you equate it on a per gallon basis, you could be paying anywhere from 10 cents to 20 cents per gallon of digestate discharged to the municipality. So again, on an annual basis, you're talking about millions of dollars. So based on these economic examples, it is almost always more cost effective and more holistic to build a digestate treatment process on site. So here we have a list, and I'm going to say it's a brief list because it's not all inclusive, of all the parameters that we evaluate and go into our design. So the point of this slide is to show how many variables that we have to process, that we have to think through. Any variation in these parameters or these variables can impact our design and therefore impact the cost or the efficiency of the process from one project to the next project. So let's take COD and nitrogen as an example. Starting with COD, we can either choose to put COD to use, or we can let it be a nuisance. So the strength of COD in relation to the strength of the nitrogen can drive whether we have to add oxygen to the process and aerate, or whether the COD can be used in a denitrification step to help remove nitrate. In many occasions, even though a site may not have a nitrate-based permit, it may make more sense to use a denitrification process to improve performance and reduce operating costs versus aerating the COD or even adding filtration step at the end of the process. So similar, TKN and ammonia drive how much aeration is required and how much nitrate may be created. More ammonia means more nitrate in biological systems, so more nitrate means more carbon is required if we use a denitrification process, or perhaps it means we have to add additional filtration, as nitrate can be filtered, but ammonia cannot. So the examples go on and on. When we get into the ionic activity, this can impact how we aerate the system, or if there's going to be a negative precipitation, or if there's going to be excess scaling, et cetera, et cetera. So all of these factors change from project to project, so we're forced to evaluate various technologies project by project. So now that we kind of understand all the parameters that go into it and how they might impact system design and our thought process, let's look at all those technologies that we can use, how, when, and why they're going to be suitable for your project. Okay, so quickly before we jump into the various tech, I'd like to provide a quick reference list for the terms and acronyms that you may hear me mention on the next few slides. So please feel free to use this slide as a reference. Okay, so we have made it. Finally, we can talk about the different technical options available. So let's go through one by one, and then we'll put each of these under a microscope on the next few slides. So let's start with DAF, clarification, and screw press. Pending the type of digester that's being utilized, it's common to have a digestate with a total solids ranging from 30,000 to 40,000 milligrams per liter on the high side. So in other words, that's basically 3 to 4% solids. In many cases, we can actually take this type of digestate directly to a solid separation process, so we can better manage the solid content and optimize how we treat the liquid content downstream. So DAFs are commonly used to concentrate the solid content up to 6 to 8% in some cases. Screw press can generally increase solid content to 12 to 18% in some cases. The point is that this step is often used as the first step in digestate treatment because it allows for an optimized biological or filtration system downstream. So next we have membrane aerated biofilm reactor, or MABR for short. Basically, forget everything you know about membrane-based biological treatment because the MABR process is completely different. This process has ultra-low energy consumption because it's able to combine aerobic and anoxic conditions within the same reactor. We'll talk about that more in a minute. It's highly effective when it comes to nitrogen removal. Next, we have NitroSax. Funny name, but it means a lot. Anytime we're dealing with highly contaminated digestate, that is extreme COD or extreme nitrogen values, it's often more cost-effective and user-friendly to operate a shortcut nitrogen removal system. So these systems are operated such that we favor one species of bacteria over other species, and we eliminate certain biological steps to streamline the treatment process. Next, we have NitroStep. For modest digestates, let's say, there's really nothing safer or more simple than NitroStep. Very tried and true process, perhaps one of the most widely used nitrogen removal processes in the world. We'll go over that in more detail in a minute. Then we have precipitation. So going back to the discussions on ionic activity, sometimes uncontrolled precipitation occurs due to the combination and the concentration of the pollutants in these systems. Other times, we actually need to purposefully create a condition prior to a biological system or prior to a filtration system where we are proactively removing these pollutants before they can cause possible scaling or fouling issues downstream. So lastly, we have filtration. Filtration can range from MBR, different from MABR, all the way to ultrafiltration and reverse osmosis. In some cases, MBR cannot be used due to scaling or overload or energy, as an example. In other cases, it's better to use RO to possibly capture nitrate instead of doing it in a biological nitrate removal system. So it really all depends on the goals and the scale project by project. So now that we understand at a high level, let's go through each of these technologies one by one. Digestate tech number one, MABR. So let's talk about MABR first. So MABR is a relatively new name in the industry, but it has been around and proven for well over a decade. So the easiest way to think about this is picture a closed membrane where we inject oxygen to the inside of the membrane. So only oxygen is allowed to diffuse through the membrane from inside out. So this creates a perfect condition for autotrophic bacteria, i.e. nitrifying organisms, to develop on the membrane surface, and we refer to this as a biofilm. This occurs, number one, because autotrophic bacteria love protected surfaces and static surfaces, and number two, they require a high oxygen gradient to promote growth and ammonia reduction. For those of you who know anything about biofilm-based systems, they can be highly robust and provide added stability because essentially the bacteria always remain fixed within the reactor, and they tend to self-regulate. So these units, these MABR units, are placed inside of a reactor where the bulk liquid condition is actually anoxic. So as the biofilm begins to oxidize ammonia to nitrate, the nitrate is combined with the COD or the BOD in the bulk liquid where simultaneous denitrification occurs. So this is where we get our low energy consumption from. Only air goes to the nitrification process. Since this is a passive aeration process, it's much easier to diffuse oxygen at much lower pressure, much lower energy to introduce oxygen directly to the biofilm. So the beauty of these systems is that it's highly effective at total nitrogen reduction compared to, say, conventional treatment or an MBR process. The energy consumption is typically less than half of other systems, so highly effective in that regard. The main disadvantage to this tech is that there is an upper limit to the COD and nitrogen ratio. This is because the heterotrophic bacteria, that is the bacteria responsible for nitrate reduction and COD reduction, grow much more quickly than autotrophic bacteria. So we aim to prevent the buildup of unwanted bacteria on the membrane directly. Okay, so the second digestate technology I want to talk about is NitroSax. This is likely a name that most of you have not heard of, so I'll explain what this means. So This technology is a modified Sharon process. For those of you that do not know, Sharon process is a shortcut nitrogen removal system using suspended growth only. So there's no attached phase, there's no biofilm, there's no membrane. It is suspended phase bacteria only. So these systems are typically designed as step one in a more complete biological system. And the way these systems are operated is the pH is controlled and the ORP is controlled within a specific range such that we can control the growth rate of ammonia oxidizing bacteria and we can suppress the growth rate of nitrite oxidizing bacteria. So this becomes very powerful because this directly impacts the energy requirements of the system. As most of you know, when ammonia is oxidized, it's a two-step process. Typically, you're oxidizing ammonia to nitrite and then nitrite to nitrate, so nitrate being NO3. So that final step from NO2 to NO3 is what requires an additional 40% in terms of energy and oxygen supply in these systems. So by managing the pH, the ORP, and the oxygen supply, we can suppress how much nitrate, NO3, is actually produced in these systems. So what we're left with is primarily NO2. That NO2 can be directly denitrified, or we can filter it if we desire. So the benefit of this technology is that it can accept high COD, it can accept high nitrogen loads. There's really no upper limit to the ratio. And it's reasonably flexible with ionic activity, so calcium and things of that nature. The main disadvantage is that we typically only design for 40 to 60% removal efficiency with these systems. Like I said, it's the first step in a more complete biological system. The reason we don't design for more than 60% removal efficiency is beyond that, it becomes difficult to maintain the proper biota in the system. So for this reason, we often add secondary biological treatment or even filtration after this type of process. So this could be an MABR, as we've already discussed. This may be an MBR. This may be a more conventional process, etc. So we'll talk about these other technologies in the upcoming slides. The final digestate technology that I want to discuss with you guys today is called NitroStep. So this is essentially a conventional biological process designed with the strength and the variability of digestate in mind. Most often, this is designed as what's called an MLE process. So that's a modified Ludzak-Edinger process. Basically means we have a pre-anoxic tank followed by an aerobic tank. As the ammonia is oxidized in the aerobic tank, it is recirculated at a high rate back to the pre-anoxic tank. The benefit of this pre-anoxic phase is that, number one, we're going to consume a lot of BOD and COD here with very little energy. Number two, the process can actually generate alkalinity, which can help reduce external chemical requirements. And number three, we're further decreasing nitrates, which allow for a much more effective biological solid separation step downstream. As a side note, too much nitrate in clarifiers is a big issue. It actually can degas or off-gas, basically create nitrogen gas if you're not careful in the sludge blanket and cause sludge to float. So these type of systems are often combined with other systems like the nitrogen shortcut that we talked about on the previous slide, or even ultrafiltration, or even reverse osmosis in some cases to capture that final nitrate. So the main disadvantage of this process, it really comes down to size. It is a lower rate process, and this requires more volume. But that said, it is a very stable process, and it's one of the most widely used processes on a global basis. So the main cost for this process is typically the tank itself. Okay, so generally I try to keep these tech talks at 15 minutes, but I think we went a little overboard this time, so I apologize. So let's wrap it up. In conclusion, let's just say that digestates are fun, but they can be complicated situations. We've learned that we can extract value from digestate, but there may be situations where nutrient removal over nutrient recovery may be required. We also learned that no two projects are ever really the same, so it's best to keep an open mind when considering digestate treatment options. Hope you enjoyed this one. Please join me next time for Tech Talk number 3, where we will take a specific look at meat processing operations and how to create value from their byproducts. Until next time, thanks and keep it clean.